back to NCERT Magnetic Effects of Electric Current. Children, in the previous class we studied about electromagnetic induction means what. Under the activity of it we have came to know due to a motion of a magnet an induced electric current is produced. So children, with this previous knowledge, in today's session we will learn that is, if a moving magnet is replaced by a current carrying coil and the one more coil, which is how it is going to vary due to change in the current of a first coil. What happens in the secondary one we will see. So in order to understand is the construction we have to study first, isn't it children? For example, if you want to perform an activity means first thing we want to know what are the materials which we are going to use for that, isn't it? And the second is how to set up. Here the materials simple children. Here two coils we needed here, means two different coils consisting of a large number of copper wire turnings. We want nearly 50 to 100 woundings we have used to make children. Here we will name the first one as a coil 1. It is also called as a primary coil. Understand children? The coil 1 is also called as a primary coil. And the coil 2 can also be called as a secondary coil. Isn't it? See what we did? We have named them as a, this is what? One coil, and this is what? Another coil. We have named first coil as a coil 1 or primary coil, and the second coil as a coil 2 or secondary coil. So here the two ends of the first coil has to make a series connection with the battery and a plug key children, isn't it? Looking children here, the two ends of the coil 1 are connected, one end to the battery, the another end of the coil is just connected to the plug key, isn't it? This is what one part we have completed. Now how the two ends of the coil 2 has to be connected? Very simple children. The two ends of the coil 2 are connected to the galvanometer. Understanding? Two coils we have taken and which are wounded upon a non-conducting cylindrical roll children, isn't it children? Upon that what we did? We have placed the two coils. The first coil ends are connected in series with the battery and the plug key, whereas the two ends of the coil 2 are connected to the galvanometer. So after making these all arrangements, now we have to plug the key. In the first coil, what we have to do children? We have to switch on the key in the first coil, isn't it children? That is when you switch on in coil 1, what happens? An electric current starts flows, isn't it children? As soon as the current starts flowing in this direction, the magnetic field will start moving, isn't it children? Means around the first coil, now we can find a magnetic field lines, isn't it children? What happened? Here all what we can find? A magnetic field lines we can find, because we have already studied when a current carrying conductor produces a magnetism means there exists a magnetic field lines, isn't it? So here when the current starts flowing from the battery, there exists one magnetic field lines across it, means around this coil we can find a magnetic field lines. So when the current has started flowing in the coil 1, it has experimentally found that children, we have found a small deflection in the galvanometer of a coil 2. We have not passed any current to the galvanometer, but why it has shown deflection? Only we have connected to the galvanometer. Here means we have connected to the battery, through that the current is flowing, we can come to know. But here we are not done that all. But why the galvanometer is showing deflection? You know children, the main reason is that when the current starts flowing in the first coil or primary coil, a potential difference will be such change, isn't it? Due to change in this potential difference, a magnetic field also changes in the first coil, isn't it? Due to this change in the magnetic field of a first coil, the magnetic field of a second coil also changes. Not understood, children? Okay, I'll say here all one magnetic field is there, and this coil surrounding also magnetic field lines will be there. When this line changes means magnetic field line of a first coil changes means what happens? It makes a change in the magnetic field of the second one, isn't it, children? Because of that, the galvanometer has shown deflected. When the current is flowing in the first coil, the needle has started deflecting to one of the side, isn't it? And immediately it comes back to the zero mark, isn't it, children? It is showing a small momentary deflection and it will come back to what? A zero mark. Okay, we will take that is when current starts flowing in coil 1, isn't it? Galvanometer of coil 2 started momentary deflection. Understood, children? It means that when the current starts flowing in the first coil, we have found a momentary deflection in the second coil. Okay, now we will disconnect this battery from the coil 1, isn't it? What we did? We have disconnected, means we have removed, isn't it? Switch off, we did disconnect the battery from the coil 1, isn't it, children? We are removing this battery from the coil 1, disconnecting this battery from the first one. Again here the galvanometer started deflecting, but here in the opposite direction. What happened, children? Galvanometer started momentary deflection towards opposite end or opposite side, isn't it, children? Imagine that when the current is flowing in the first one, that is coil 1, it has deflected towards right. But when you are disconnecting the battery from the coil 1, the galvanometer is started deflecting towards left and it is coming back toward zero mark. So what we have understood with this activity, children, whenever there is a change in the potential difference of a first coil, we have found that an induced current has produced in the second one. That is how it is possible. Means when a magnetic field associated with the first coil or primary coil, when it changes means the magnetic field associated with the another conductor, means another coil also changes. Due to this change in a magnetic field of another conductor, we can produce what? An induced electric current. What we have found, children? An induced electric current is produced. Due to what? A change in the magnetic field of a first one, isn't it? Due to a change in the magnetic field of a first one, brought a change in the magnetic field of a second coil or conductor. And because of this reason, an electromagnetic induction has produced. What electromagnetic induction will tells us, children? It is a process where we can bring that is due to change in the magnetic field of a first conductor, we can produce an induced current in the another. So the same thing happened here. We are making a magnetic field that is changed in the first coil. We are producing an electric current in the second coil. Isn't it, children? Is this an electromagnetic induction? Isn't it? The same concept we will use for working of a generators, children. In many practical cases, it is often convenient to either bring a moving coil towards a magnet or to bring a magnet towards the coil. But so far we have, it's our convenience, means as per our convenience, what we will do means, in many practical situations we will bring a moving coil towards a magnet. Means the same principle we will use in our generators. It means that here the induced current produced by this method will be highest when the direction of the magnetic field is right angles to the direction of the motion of the conductor. Isn't it, children? For example, imagine that this is one motion of a conductor and this is what magnetic field. When these two are at right angles, means we can find a highest induced current. Means we can produce a high amount of an electric current. So how can we know the direction of an induced current here? There comes a special rule called Fleming right hand rule. Okay, children, now let us study what is Fleming right hand rule. Now we will study how to find the direction of an induced current and which rule we have to use there. Suppose in order to find the direction of an induced current, we have to apply what? Fleming's right hand rule. Isn't it, children? How we, in the working of an electric motor, which rule we have used? Fleming's left hand rule. Isn't it? In order to know the direction of a force, we have used Fleming's left hand rule. But here, in order to find the direction of an induced current, we have to use Fleming's right hand rule. This Fleming's right hand rule widely we will use in our electric generators, children. Okay, we will study how it works. That is, when we stretch the first three fingers of our right hand, that is, when you stretch the thumb finger, forefinger and a middle finger of our right hand, such that each one of them should be what? Perpendicular to each other. And here, the thumb finger is giving the direction of a motion of a conductor, children, here, isn't it? The thumb finger, what it will give? The direction of a motion of a conductor, whereas the forefinger or index finger, it will give the direction of a magnetic field, and the middle finger will give what? The direction of an induced current. Got it, children? Okay, better here I will write. That is, thumb finger, isn't it, children? Thumb finger gives direction of, it gives one direction of motion of a conductor. Motion of a conductor. And the next one, forefinger or index finger gives what? Direction of a magnetic field. Similarly, what? The middle finger will give the direction of one induced current. Isn't it, children? The direction of an induced current is given by what? Which finger, children? Middle finger. Okay, once again I'll repeat, children. When we stretch the first three fingers of our right hand, such that each of them should be perpendicular to each other, here the middle finger will give the direction of an induced current, whereas the forefinger or index finger will give the direction of a magnetic field, and the thumb finger will give the direction of a motion of a conductor. And this simple rule is called as the Fleming's right hand rule, where we have to use, children, in electric generators. In electric motor, we are widely using what? Fleming's left hand rule, isn't it, in order to know the direction of a force, whereas Fleming's right hand rule we will use widely in our electric generators. In order to know the direction of an induced current, Fleming's right hand rule should be used. Got it?